Well, all right. Hello, everyone, and thank you for joining. We're right at our start time here, so I thought I would introduce Dawn. We have a riveting webinar for you today with all of your amazing questions. We will call out a few at the end, and certainly if you have them ongoing, you can throw them in the questions and answers, and I'll try to respond as we can, and we'll call them out at the end. So without further ado, Dawn, go ahead and kick it off.
Okay. Guys, this is one of the questions that is probably the most frequent question that we get. How do I aim my antennas? How do I place my antennas? So we're going to tackle this. I guess we've talked about some of these things, but we're going to try to put them all together and maybe they'll make a little more sense and kind of click the gears in place in your head. So why are we putting up antennas and what do we expect to do with them? I got to go back to this. This is the number one priority for everything we do with wireless microphones. The engineers work very hard to make quality wireless mics, and to make them work out of the box, you have to achieve this capture effect. You have to get a signal about 20 dB stronger than whatever your residual noise is, wherever you are at that frequency. And when that happens, your microphone locks on to that frequency and stays locked on. So what we're going to talk about, first we're going to talk about some best practices for antennas, because if you put them in the right place but you do it wrong, it doesn't much matter, right? So the first thing we have to remember is that radio waves move in straight lines, at least at the distance we're talking about. If you're talking about getting the other side of the world, then we got to take into effect the curvature of the planet, but we don't have to do that at 100 feet. Okay, so the radio wave is going to move in a straight line from the transmitter to the receiver, hopefully. That's what we need to make happen. So the first thing we have to do is we have to maintain line of sight. Your transmitter needs to be able to see your antenna. You can't put it in a closet. You can't put the antennas inside a metal rack because you almost obliterate the signal. So you can't put the antennas in another room. Your chances of getting it to work are very slim. So just imagine, that the transmitter was a gun sight. When you put it where it's going to be, you need to be able to look up and see the antenna. You can't go around corners. There is a distance too that you need to be away from the antennas, both for wireless mics and in-ears. And it has to do with the relative strength of the antennas. And these are absolute minimum distances. It might even need more than this. But what happens when you get too close, it's just like mic and a guitar amp. If you stick a microphone 10 feet in front of a guitar amp, it's going to be a whole lot different than 2 inches, right? Going back into your board. So the closer you are, the stronger signal you get in the antenna. And it's very easy to overload, clip the front end of the receivers. So we've got to maintain a little bit of distance here. And the tighter your pattern is, the farther it goes. So these are the basic kind of antennas we're probably working with. And you can see, the relative distances, but realize if you're having problems and you're really close to your antenna, that could be the problem. Easiest thing to do is back up 10 or 20 more feet and see if you still got the problem. Okay, so we need to get rid of these antenna farms. If you're using a whole bunch of antennas like one of these things, you are tying one or both of your hands behind your back, and getting it to work is going to be very difficult because the antennas generate a magnetic field, and when they're this close to each other, and I mean this close, I mean closer than 6 feet, the magnetic field jumps into the next antenna, producing noise, so we're raising the noise floor. That's what we're trying not to do. Also, when you put antennas together, you create array, like line array speakers. This diagram at the bottom is just showing if you had 2 whips and you get them somewhat close together, instead of getting the nice circle that you would expect with your whip, you get lots of lobes. So you're creating hot and cold spots across your stage. So we want to avoid having lots of antennas, use a distro. And the last thing is it's difficult to aim your antennas. So to maintain polarization, which gives us a nice strong signal so that that signal is more than 20 dB above the noise floor. The noise floor is there no matter what. So we got to get the signal above that. So we got to be able to aim these antennas. Typically, the best place for an antenna, a directional antenna, is just above head height, somewhere 6 to 10 feet above the deck. Something that's very difficult to achieve, but you'd like to mount it off the wall a little bit. If you can get it a couple of feet off the wall, it makes for kind of a funny looking installation, but you can see that in that diagram that when you've got it right up against the wall, it slightly changes the frequency. So the frequency you think you're transmitting at moves just a little tiny bit. It still works, but so this will not kill you. This will put one more straw on the camel's back. So if you can, we'd like to move off the wall a little bit, especially whip antennas are really bad at this. Directional antennas are mostly dead on the backside, so the effect is much less on a directional antenna. But if you're putting a whip antenna up against the wall, you're really handicapping what it could do. Also, I see a lot of people, they'll mount their antennas up in lighting truss. And it's the same thing. That lighting truss is like your wall. So if you look at this, you can see down on the bottom a whole bunch of CP beams for in-ear monitors for this particular gig. They can be mounted right up against metal because they have a back plate. But typical, omni antennas and directional antennas like we've got on the top, you want to lift those up at least a couple of feet off the metal. So it may be a convenient place to put your antenna, but you are handicapping it at least a little. This is not a go, no go, but this is, you're not getting the best out of this antenna that you could. So we want to get the best we can. We paid for it. We might as well get everything out of it that we paid for and not give any of it away. So this is something else you want to keep in mind when you're mounting your antennas. So let's talk about aiming antennas. So if first you have to figure out what it is you're trying to cover. In a perfect world, your antenna would only cover your one wireless mic and nothing else, but they have patterns. They pick up, more than just that. So are you trying to cover a large area, or are you trying to restrict your coverage, like let's say just to a stage? So you have to think about what it is you're trying to do, because that's gonna make a difference in what antenna you select and how you point it, how you aim it. Pardon me. Okay. So the first thing we got to talk about is omnidirectional versus directional antennas. Think about it like omnidirectional and directional microphones. I have 50 microphones. I probably have 2 omnis, and they don't come out of the box very often, but when they're the right tool for the job, they're absolutely the right tool. So if you have a little theater, something like this, and you mount your antenna on the back wall, be an omni or directional. If it's directional, it's going to point in the direction of the stage, if that's the way you've got it. If it's omnidirectional, it's pointing at the stage, but it's also pointing behind the stage. So we're going to pick up what's behind the stage, the other direction. Now, even if there's no, wireless mics there, what you're picking up is additional noise, because you're picking up everything, where with a directional antenna, you're only picking up in one direction. So to make this really simple, just consider that you're getting half as much noise because you're only looking in one direction. Assuming the noise is evenly dispersed, which it normally is unless you've got, an X-ray machine sitting in the back of your hall or something. So when you use an omnidirectional antenna, you can expect a 3 dB gain in your noise floor. So, but if that's what you need to do, if that's the right tool, so for something like this, where I want to cover everything, I have to mount my omni antenna. Omni antennas should be placed in the middle of your coverage pattern, whatever you want to do. So if you want to put an omni in your in your theater and you want to cover the entire theater, it goes in the center. That's where it needs to be. If you just want to cover from the back of the hall to the stage, then you want to use the directional antenna. So Omnis are generally good outside. I don't know why, I seem to be working with a lot of golf clubs lately. And they have a system indoors, but they want to be able to pick up stuff outdoors. And if you put an Omni antenna on one of the corners of the building, you get 270 degrees of coverage. So it's picking up everything kind of in one direction. So that's when it's absolutely the right thing to use. I generally use Omnis outdoors and generally directional antennas indoors. And most of the time I'm working indoors. So, just a consideration, picking the right antenna to start with. So we know our whip antennas are Omnis, right? The little whips that come with your wireless mics are omnidirectional in the horizontal plane. So you need to look at the coverage pattern, just like you would look at the pattern for your wireless mic. Is it cardioid? Is it supercardioid? Hypercardioid? Omnidirectional? Is it a shotgun? So they all have polar patterns, right? So mostly we're interested in the horizontal, because most of the time we're not picking people 50 feet up in the air and flat on the ground at the same time. Although I did have a guy with circus acrobats the other day telling me about that. He's got people climbing 30 feet up in the air. Okay, so really what we want to see is the azimuth, the horizontal polar pattern. That's really the one that's important. So when you look at this, imagine that you're standing in the middle of that dot in the center, looking straight north. That's the way these things are usually looked at. So we call this bore sight, like a gun. So that's what you're looking. So as you're laying this pattern over your auditorium or whatever it is you're trying to cover, understand that's what it's going to pick up. So even a directional antenna, you can see it has some pickup on the backside, down south. It still has pickup, but if you're reading that chart, it's 1% of what it is going forward. I know it's in dB, but that's 10 dB down is 1/100th. So it is picking up from behind it, but not very much. Basically, it's picking up in front of it, right? And the coverage goes in that kind of balloon that's drawn there. So understand that it doesn't just pick up in that direction. It picks up in all directions, but it gets weak if you're not looking forward on it, right? So kind of look at it this way. The pattern right in front has more gain. But as you go off to the sides, it's still picking it up, but with less gain. So if you're closer to the antenna, so if we had a long, narrow room, right? So straight down that room, across the long way, you want to point your antenna because you get the most gain at the back of the room. But as people come forward closer to your antenna, they're off to the side, they're off axis, but they're closer in distance, right? Because the signal fades with distance, 6 dB per doubling, just like speakers do. But you're still getting coverage out to the side. You just have to look at the 3 dB, that's the half power point, and understand what it is you're trying to cover. Is that going to work? So like I said, because you're getting closer to the antenna, you don't need as much gain when you're closer to the antenna. Just for giggles, I found this is a typical stereoscopic view for humans is about 120 degrees wide. So if you're standing where you're going to put your, so in a typical paddle LPDA type antenna, typically is 120 degrees wide. They vary a little bit. So basically, if you're going to put your antenna in the back of the hall, put your head against the wall, look forward, and that's what you're going to cover. You don't have to get out the, you don't have to measure it. That's what you're going to get. So The next question I always get is how far is it going to go? And how far it goes isn't really just dependent on the antenna. It's a factor, along with a lot of other factors. So to figure out how far an antenna is going to go, we have to do what's called a link budget. We have to add up all the gains in the system, subtract all the losses, see what we got at the end, and then see, this says carrier to noise ratio, dynamic range. We have to see if we've got enough above the noise floor. We're shooting for 20 dB. So if you don't want to do all the math and all the measurements, if you just go to our website and hit this performance calculator button up in the top of any page, it takes you to this calculator, which is a very simplified way to do a link budget. So all you have to do is answer the questions in all these drop-down boxes, right? So there's a whole bunch of microphones and a whole bunch of distances and all this stuff. You just click on all these and all the math happens behind the scenes. And if you get a green light at the bottom, then you have 20 dB of signal above the noise floor. Now, this is telling you that it's working for one microphone. If you bring out 20 microphones, they interfere with each other and you're going to have to do channel coordination, which there's another button for that we can now do, but we'll not go there for right now. So basically what we need to know is that our signal is going to have at least 20 dB of level above the noise floor. So I would, click this for everything you do and get an idea. It might still work. So if you're right at 20, you get yellow. If you're below 20, you get red. It might work when you get red, but I sure don't want to be there. I'd be very nervous. So it's best to kind of work these things out beforehand, and you might have to switch to better cable or make some other choices if it's not going to work for you. But we need to get that level out there. So this is talking about the width, the horizontal width of these antennas. So these are the typical kind of antennas that you're going to find, or some variation of these. So we have a whip antenna that comes in a box with everything. It essentially has no gain, and in a horizontal plane, it covers 360 degrees. It is, however, like a donut. It has a lot of loss above and below. So the patterns, we talk about omnidirectional, but really we just mean that in the horizontal plane. Then you have paddle type antennas, LPDAs, and they're typically 120 degrees wide with about 5 dB of gain. Because we take what would have been the back area and we're not going to pay attention to it, so we cut that off and we add it to the front. That's why it's got gain. It's passive gain. And then we have helical type antennas, mostly used for in-ear monitors, and typically they're much tighter. They're very focused. And so because they're twice as focused, they have twice as much gain. So about 10 dB of gain on these guys. And you can see from these gain amounts, that's why you need to be farther away from the higher gain antennas than the lower gain antennas, but you need to kind of stay away from antennas. You don't want to get too close. Okay, so now we get to the fun part. So say you've got, this is kind of a typical looking auditorium. And what are we going to do? Well, most people right away go to, we're going to put the antennas back at the front of house mixing position somewhere on the back wall like this and point it towards the stage. Okay, good. So what's going to happen is you're going to cover that direction, a little bit behind it. If you had an Omni, you'd be covering that far in the other direction too, which we don't want to do. But this is typically how people do things. It's also, if your equipment's back there, having shorter coax runs means you're going to have less loss. So again, back to that performance calculator thing, that's going to give you more gain. So this is one place we could do it. It's going to be slightly weak in these corners. it's probably still going to work because you don't have much distance, right? So because you're pretty close to it, the fact that the antenna is weak in the corner, but the requirement is usually less. But this is also good. Think about it. I see a lot of churches now where they're doing, and other shows where they're doing audio and video. So if all your camera guys are back in one of these corners, who knows what garbage they're putting out, but we don't want to pick it up in our antennas. So this is a fairly good way to do it and somewhat isolate at least a little stuff that's in the corners. However, if you want to cover this entire space evenly, if you put it in the corner, so we've got, in this case, a rectangular room. We've got 90-degree angles, right? If we put a 120-degree antenna in there, it's going to cover that entire space from any corner in this room, provided you don't have a wall in front of it. So the very back corner, in the upper right-hand side, there's if you put it right there by the exit sign, there's a little wall, that for the stage, so that would block some of it. But in the back corners, if this was a meeting room, it didn't have a stage, it just was a big room like a hotel ballroom or something. Corner placement is going to make sure that you cover the entire area in the pattern. Now, you can also move the antenna up. Sometimes the mixing position's farther up, and that's fine. You're still going to cover the stage, just you're not going to cover behind you. So this actually, if you have a mixing position that's farther up and you move it up to be there, this could be a good thing. Because unless you have a situation where you have an actor or a pastor or something that walks all the way to the back of the hall. If he walks all the way to the back of the hall, you're going to have to check your antenna coverage because it's going to be weaker. It still may be enough. You have to walk test it to find out. And lastly, people that put their stuff up on the truss. So this makes a lot of sense to do that if what you want to cover is the stage. And no, I don't want to cover all the people in the audience with their 5G phones in their pockets. So this is a real good placement if you only have to cover the stage. But if you have actors that walk in from the back of the room, you're not going to get them until they get, well up towards the stage, right? So you just think about what it is you want to cover. I think it's interesting when we first introduced our diversity Omni antenna, people are going, oh, great, I can cover everything. It's like, but you don't want to cover everything. If you had a microphone, use a cardioid mic, you point it at one singer. I don't want to pick up the whole band, and I don't want to pick up, the hecklers in the audience. I just want to pick up the guy that's speaking or singing. So I'm using a rather focused mic at him. So think about what it is you want to cover, and you don't want to cover anything but what you do want to cover, right? You can't just dial that off, but you want to think in those terms. I really only want to cover what I want to cover, and I would like to ignore as much of everything else in the world that I can. And then another possibility would be like in one of the wings of the stage. Again, good. If I need to cover the stage, this is a great way to do it. But you can see what my coverage is going to look like out in the hall. So if you can live with that, or you desire that, again, if all the video equipment was up in the top left kind of corner of that room, I'd be ignoring it. That would make my signal to noise ratio get better. So you just have to kind of understand what's going on around you when you think about how to aim your antennas. So as you can see, there's a bunch of ways to do this room. You're going to get little varying results. And the truth of the matter is, most times it probably won't matter. You will go up and down a little bit in that carrier to noise ratio. So if you're close, it's going to matter. If you have more than enough, And most of the time we have more than enough. It's just those little aggravating second and a halves where it drops out, where you don't have enough because somebody did something that you hadn't planned on when you set this up. So these are all perfectly valid locations to put your antenna in this room, depending on what it is you're trying to cover and depending on what it is you're trying to exclude. So that's the part I guess maybe people don't think about right away. I have an area I want to pick up, but I want to exclude everything else. So how can I do both of those things? That's kind of the choice you need to make. I want to talk about ceiling mounted antennas. So when I put an antenna, I put an antenna on a wall in the back of this room. It's going out in every direction for, tens of thousands of miles, actually. It gets weaker. It's so weak it won't work, but it's going everywhere. It just goes, right? It doesn't stop. If I mount an antenna on the ceiling, you got to remember that it's got a pattern and it's going to spread out. So the amount of spread that you get depends on the ceiling height, right? So again, am I trying to exclude something or am I trying to include something? So again, you might want to put, if all you want to cover is the stage, a ceiling mounted antenna 20 feet high is probably going to give you 50 or 60 feet of primary coverage, right? It's not going to work for a 100-foot stage. You're going to have to be taller. So you have to think about what the pattern of your antenna is. Is it round? This would be an Omni, would be round. If it was a paddle, it's going to be a rectangle. So sometimes you have to do this. We get people that do casinos all the time. And now, slot machines have the video walls, and slot machines are 8 feet tall now. So if you're trying to go horizontally through all those machines, you've got a million little things that are blocking you. And, essentially you have a shadow behind them. So sometimes ceiling mount is exactly what you want to do. And you can cover and you can exclude more, right? So sometimes that's what we need to think about, what we need to exclude. So ceiling mount certainly is an option, but just understand that I'm going to have a pretty tall ceiling to cover this whole space. I don't even know what the dimensions are, but this is all proportional to the ceiling height. Roughly like 3 feet radius per 1 foot of ceiling height. So with a 10-foot ceiling, you probably have a 30-foot radius, something like that. It's going to depend on your pattern, but that's going to be probably a reasonable guess most times. Okay. So now what happens when I have a room that's not rectangular or square? I have an oddball shaped room. Sometimes we have curves, we have all kinds of things. But we need coverage everywhere, right? So again, we got to remember the radio waves travel in straight lines. So if I put my antenna over here, it's gonna cover straight across, but you can see that the wall, that corner is going to block me, and so I'm going to have an area at the bottom of that where I have no direct coverage. Now, the yellow line is hitting that back wall, and it's going to bounce down into that other area where it's going to bounce off the wall, and it's going to look like a pool ball bouncing all over the cushions on the table. You may have enough signal. If you have well more than that 20 dB of dynamic range, this could work. It depends on size, it depends on power, it depends on a lot of things, but you will eventually get a radio wave that's just got to bounce a whole bunch of times, and every time it bounces, it takes a lot of power out of it. So you're not getting a direct signal, you'd be getting an indirect signal down in that area. So depending on how, maybe that area is not necessarily important. And in fact, if there's junk down in that area that I don't want to get into my signal, then this actually is a good placement. And if all the people are sitting up there and down on the bottom is the cafeteria or something, and I don't particularly want to pick that up, as long as your customer doesn't need to pick up everywhere, this could be a good choice, but just understand what you're getting. Likewise, if we put it on the other side of the wall, same thing's going to happen. We have an area at the bottom that we're going to have to depend on a lot of reflections of our signal to get there. So we still have some signal. It's just weak. Is it weak enough? It depends how far above that 20 you are. If you're at 40, yeah, it's probably fine all day. If you're just barely above 20, it could be iffy. So just, thinking about that, where do I want to cover? Where do I want to exclude? Now, one of the things I see people do all the time that they really shouldn't. And again, if you get away with it, then you got away with it, right? If it works, it works. You could do everything wrong, and if it works, it works. Done, right? But if you have two antennas, so like you've got two paddles, people go, well, I'll put one going this way and one going that way, and I'll cover the whole room. You will cover the whole room, but what will happen is you only have diversity where they overlap. You may not need diversity. Diversity is it's actually a bad thing sonically, but you got to stay on the air, right? So it's better that you have less than perfect audio and you can still hear somebody than you have zero audio usually. So when you have your antennas each cover a different zone, the only place you get diversity is where they overlap. So like this, if this was a basketball court, I guess people think, well, maybe my antenna won't penetrate all the way down to the other end, so I'll put one at the other end and make it go back. And the answer is yes, you will have coverage everywhere, but you only have diversity where they overlap. And it's not a hard line like this. It's going to kind of fade out. But this is just something to think about. Really, when you are using two antennas, if you're using two paddles or two whips, they need to be 6 feet apart. Just do that, and they need to cover the same area. You can't have diversity unless you have two antennas covering the same area. That's not a problem with our polarization diversity antennas, the DFIN and stuff, because they're built together. So you've always got two that are together. But if you're using separate paddles or separate whips or other things, if you do it this way, just understand what you've done. This may work all day long for you, but understand you've given up a lot of your diversity. So if you do have a problem, your receiver may not have an antenna to be able to switch to. So keep this in mind. So anyway, if you want to cover this entire L shape, if you put it in this corner, it's going to cover everything, right? Just like we put it in a corner of the rectangular room and it covers everything. So this would be the preferred location. It doesn't have to be exactly in the corner. We can make some changes due to, mechanical. There may be a pole you want to mount it on or something, a pillar or something. So we would like to be close to these. With any of these, I'm not talking exact locations. We have a fair amount of latitude to move this around a little bit anyway, because we always have mechanical considerations. You can't get a wire there, or there's some reason you can't get there. So anyway, this is probably going to be a better shot for that room. Your antennas have to be in the room with you, right? A lot of times at schools and stuff, they'll put the radio gear in a closet or something. And it might work, but this is what you can expect going through these kind of things. So I get that sometimes. I got antennas in this room, but we need to cover the little room on the other side of the wall. Is it going to work? Depends what the wall's made out of. And so what we're looking at here, it says glass, plastic, wood, brick, concrete, metal. However, wood, brick, and concrete hold water. So water and metal are our enemies of things passing through. So if you just have a wooden door with your gear in a closet behind it, and you can afford to lose 10 to 40% of your signal, which you may very well be able to do, right? It could work. If you've got a metal fire door, ain't going to work. You probably don't want to put your antennas down inside a rack. Well, when you put them on a rack, the first thing is, now they're only 4 feet up off the floor, typically. So you're going to have to go through bodies. So, that's why we want to move the antenna up over people's heads. But you can do it. I mean, just understand you're going to have some loss because you did it that way. So these are the things. I would also caution divisible rooms. They roll out those panels and divide off your hotel ballroom into a bunch of sections. There's probably metal framing inside that. If you have metal framing with 2-foot centers, you're okay. If you have metal framing with 16-inch centers, it's not big enough to let a radio wave pass through it. So on 16-inch centers, that wall is nearly solid metal as far as a radio wave is concerned. If it has a 2-foot opening in it, if it has a 2-foot door in it, and doors are 3 foot, so it'll go through that door. But if you have a sheetrock, with metal studs, they're almost all on 16-inch centers, about code everywhere. It really doesn't want to go through those walls, but it just depends how much you need on the other side. But you're going to get some loss, so understand that going in. So let's talk about antennas when we have both mics and ears. This is a definite horror story because the antennas are close together, and first of all, you got antenna farms. That's a problem by itself. But you have an omnidirectional IEM antenna transmitting power straight into your receiver's antennas. So that's going to screw things up, right? Because you've got one antenna that's transmitting, it's pitching, and the other one's catching. And it's going to grab all that signal, and then it's going to have to deal with it. So we want to make sure that we don't point our in-ear transmitting antennas at our receiving antennas. If your receiving antennas are omnis, you almost can't avoid that, right? You're going to definitely get some degradation because those antennas go every direction. So it's pretty hard to avoid. You're essentially there. But if you think about it, everybody understands this. We don't point our microphone at our speaker, we get feedback, right? Well, you don't get feedback with your radio, you get interference, but sort of the same kind of principle holds. So if you just remember that, everybody's pretty good with this. But if you have a transmitting and a receiving antenna, you want to not point them at each other. Now, it's an advantage, and it's hard to take advantage of, but depending on how you mount this stuff, if you put your in-ear transmitter antenna behind your mic antenna, like the top, then you're blowing right straight into it, right? If I do it the other way around, if my microphone receiving antenna is behind my in-ear transmitter, remember, the waves are coming through it the other direction from your wireless mics, and that really has nothing to do with the fact that you're transmitting in-ears the other direction. So if you can put your wireless mic antennas a couple of feet behind your in-ear monitor antennas, then you'll pick up some additional stability. Again, not a deal breaker. We're always dealing with the straw that breaks the camel's back. So we're just trying to keep as many straws off as possible. This is one thing. If you can do this, this is kind of hard to do. Side by side is actually pretty good. 6 feet apart. So if you put them both on the same wall, 6 feet apart, you're probably in pretty good shape. So we don't want to point our in-ear transmitter antenna at our wireless mic antenna. So if our wireless mic antennas are on the back wall and we put our in-ears in a wing at 90-degree angles to each other, they pretty much ignore each other. Or we can put them both in the wing, go in the same direction. And that's just fine and dandy too. What you can't do is put one on one side and one on the other. Okay, this is a recipe for disaster. And again, I see this too with people that, oh, we're going to put one paddle on one wing and one paddle on the other wing. Like, no, well, you don't have diversity to start with. And then you're pointing your transmitter at least one of them. So that's not a good solution. I would recommend that you don't do that. Or they could both go on the back wall, right? So when you got in-ears, if you got in-ears and mics, they either need to be on the same wall or they need to be angled 90 degrees apart, as close as you can get to that. They just can't be 180. They can't point at each other, right? That's going to be a problem. So here's kind of it in a nutshell. The antennas, you got to have line of sight. You got to be able to see your transmitter. You want to pick an antenna that's a pattern that's going to be beneficial to what you need to cover. Then you point the antenna at your transmitter. Well, that's pretty easy if a guy's standing behind a lectern on a stage, because that's where he's going to be. If he's also going to walk across the stage and walk into the audience and walk behind you, that's a whole different problem, you know? So understand what it is that you're trying to cover, because we're trying to not cover anything else. And sometimes the only solution for that would be to have a zoning system where we have multiple antennas. We try to make each one of them stay in a zone. We'll talk about that some other time. But that's another solution. So if you have a really oddball room that's curved and got things coming off it, you know, that may be the only way you're going to make that work. That gets to be kind of a more difficult situation. So I think with that, Mr. Adam, I've run out of things to say directly.
All right.
What else?
That was awesome as usual, Don. Thank you. I think you answered most of the questions that we received. That was probably by design. I know there was a few that came in this morning, but we do have one question here live, and you could probably cover this pretty easily. Can you review how log periodics work?
It's a phased array, right? So what happens is, if you ever look at your paddle, you're going to see a bunch of stripes on it. So what you have is you have a size, and then so the stripes, half the stripes are antennas and half the stripes are isolators, right? And when you put the patterns together, just like that slide that I had way back there where well, let's see. Yeah, everybody hang with me for a second. That one. So if I put two antennas the way they are here, you know, I've now got an array. I've got all these lobes off the side. That may or may not be a problem. If all I'm trying to do is capture straight north, I'm actually in good shape for a tiny area straight north, but I'm all over the place every place else. So in an LPDA, in a paddle antenna, we have multiple ones, and the space, it's the spacing that makes these lobes move. And there's mathematical formulas that make it so that they add up. It's just like your line array speakers, right? You stack them together and you get them close and keep them flat. They, instead of sending out in a point, they send out in a line. And you know, we get pattern control. So it's the same way. We use a bunch of antennas together. When we do it with, you know, the right physics and the right spacings and the right frequencies. All this stuff is dependent on frequency and spacing. And we can make those lobes essentially disappear. They never completely go away, but we can kind of get rid of them, and then we can change the shape of the fat part that's at 12 o'clock.
Got it. Excellent, Don. Here's a good one that comes up often. Are there any downsides to using an antenna that is more powerful than the situation may necessarily need?
Yes. Oh, you'd like to know why? Well, so if I have somebody with a wireless microphone and they're, let's say, 50 feet away from me, 100 feet away from the antenna, right? And that's as far as they're ever going to get. What benefit do I get if the antenna goes out to 200 feet? What I get is extra noise. 300 feet, even more noise, 600, even more, those numbers that came on a box that said your system works at 300 feet. That's that's highly qualified. It doesn't work at 300 feet in the middle of Times Square, and out in the middle of nowhere, it might work double that. But we don't want anything more than what we need. It would be the same way with a microphone. If I'm pointing a microphone at somebody speaking, and somebody's on a desk in the back of the room, well, we don't use typewriters that make noise. Doing something making noise, why would I want to pick him up as well? I only want to pick up what I want to pick up. So you consider that, and actually, the super high-end guys turn down their antennas, right? And guys that are doing arena level shows put pads. They actually weigh down their antenna so they don't go any farther than they need, because farther than they need is only going to pick up additional noise, which is going to lower your, you're going to, where are we at here? That one. This is the answer. This is what we have to achieve with everything we do. There's lots of ways around this. There's lots of things that contribute to this, but this is the single fact that keeps your microphone on the air, assuming you got batteries. You have to keep your signal up above the noise floor. We can only turn our stuff up so much, because we're limited in power by the FCC to very, very weak power, so that other people can use wireless mics when they're across the street from us. So what we're trying to do is get rid of all this noise. So I don't want to pick up any more noise. I don't want that junk on the bottom any higher. I want it lower. And that's why we use distros. That's why we use good antennas. That's why we use good cable and try to keep it short. All those things are going to lower the noise floor and increase that. Anytime we can be better than that 20, good for us, because inevitably somebody's going to do something to screw up your system. And you want to have all you can get, but you have to maintain this. So again, that's why we do everything. This is the one thing. Understand, this is what you have to achieve, right? It's like running a race. All you got to do is cross the finish line. This is the finish line. How you get there, I don't really care. If you don't cross the finish line, you don't cross the finish line. So this is the finish line. This capture effect. It's a unique thing that radios do, and that's what keeps them on the air. So burn this one in your mind, and you've probably heard it enough from me. I hope you understand this. The fundamental understanding of this makes everything else work, right? And when my signal is high enough above that garbage, my radio locks to it and that garbage goes away. So now you look at all the things that make it better or make it worse. That's what we do. So this is what we got to hit. And then anytime we're adding a new thing, we say, is it raising my noise floor or is it lowering my noise floor? And understand all those things, because we have to make a lot of compromises. But this is what we got to do. We got to cross the finish line, and the finish line is 20 dB above the noise, more or less.
All right, I think we've extended our time a little bit here. So, do you think maybe one more, Don, or do you, what do you?
Sure.
I've got tons of questions, so it's almost endless. I don't know where to stop here for you guys. All right, so let's see here. This is just a someone following up on something you said. I'm following up on the webinar on the phone, and I missed the reasons why it's not good practice clamping antennas on trusses. Would you please repeat the concept?
Right. So when you have that big piece of metal behind you, two things happen. You get reflections, you get echoes, right? So think about trying to put your PA system in the middle of a basketball gym. I can make it loud all day long, but being able to understand it, to be able to understand articulation becomes very difficult because there's so much reverb and echo in the room. But when you get close to metal, you're getting lots of reflections. That's one thing. And the second thing is when you get very, very close to it, you slightly detune the transmitter, right? So if you think you're transmitting at 500.125, and that's what your receiver is set to, if you get that antenna up to a lot of reflections, it's going to slightly change that transmission frequency. Not a lot, but it's not going to be as finely tuned as it could be. So again, we're just, if it's not finely tuned, then I can't pull in that signal, that 20 I'm trying to hit. I lose a little tiny bit of it. It's not a deal breaker all by itself. It's just one more thing we'd like to avoid. It goes to the negative side and we're trying to get to the positive side. So understanding what all these little negative things are. Like I said, unless you have an antenna with a back plane, the only one we make is the CP beam. They're not typical. You know, paddles don't have that. Paddles have some amount of back rejection. So a paddle's not going to be as bad as a whip. A whip up against it is going to be the worst. A paddle is going to be somewhere in the middle, and a helical with a back plane, or any antenna with a back plane, with a back plane, it's just there's a piece of metal on the back that says that's the end of the antenna. Doesn't work on the other side. That's what a back plane is. So there's not many antennas that are built that way. Our CP beam is, which is why you could see a whole pile of them in that picture, wherever that picture was. Where's that picture? There. They can go right up against it because the very back square of that is a big piece of copper, and so it's already up against the metal. It already is, and that's all calculated into the way it's designed. But with the other ones, the farther, I mean, they'd be better at 10 feet, but you know, at least something is something. Get them off the truss.
Awesome. Well, I think that's all we have time for. Thanks everyone for such great questions. I've never seen so many questions answered so fluidly. So thank you, Don, for that. There's a lot of information there to take in. We're going to be posting this as soon as possible on our webinar page for the people asking. So maybe tomorrow, as soon as possible. You know, it depends on what's going on. So check back if you need to rewatch this, and we appreciate your time as always. And be sure to look out for the next webinar next month. Thanks, everyone. Thanks, Don. Take care.
Yeah. Bye-bye.